Today is a big day, everybody, because today is the first day that we are going to learn a organic chemistry reaction, and that reaction is called the Sn2 reaction. I've alluded to it before, and it is always the first reaction that they teach you in organic chemistry. Why is it the first reaction? Because it is so similar to an acid-base reaction. In fact, the mechanism of the Sn2 reaction is exactly the same as an acid-base reaction. Let's take a look. So first of all, the name sounds scary, Sn2. What are those letters and numbers referring to? Well, it means substitution nucleophilic bimolecular. So we can kind of break down the parts of this name and see why it's called this. So substitution, this is going to be a substitution reaction. When we look at the reaction, you'll see why, because one group is replacing another, it's substituting another. It's called nucleophilic because the group that's doing the replacing is a nucleophile. And it's called bimolecular. We'll talk about what that means a little bit later on. We'll have to look at the Sn1 reaction, and then I think it's better to just show by comparison the difference between the Sn2 and the Sn1 reaction to show the difference between what a bimolecular and what a unimolecular reaction is. You may have learned what those terms mean in Chemistry 102 when you were talking about rates. So if you maybe remember what a bimolecular reaction is when you're thinking about rates, it's the exact same bimolecular here, but we're not going to be talking about rates much. Just keep in mind that we will discuss the bimolecular part later when we talk about the Sn1 reaction. And yes, there is an Sn1 reaction, but no, we talk about the Sn2 reaction before the Sn1 reaction. Let's take a look at what is this reaction. So in order to do an Sn2 reaction, you need a nucleophile, as the name suggests. So I'll just put a nucleophile here, and I'll give it a negative charge. So the nucleophile, of course, doesn't have to have a negative charge, but oftentimes it does. So that can be any nucleophile. We'll talk about what sort of nucleophiles are common in this reaction. And then what we need to do is have a carbon that is sp3 hybridized as the other reactant in this reaction. So there's two reactants. The first reactant is a nucleophile. The second reactant is you need a carbon that is sp3 hybridized connected to something called a leaving group. Now, there can be other stuff connected to the carbon, but all that I'm focusing on right now is this key bond between an sp3 hybridized carbon and a leaving group. There can be other atoms involved as well. This is the simplest case scenario. So Lg stands for leaving group, and it's typically going to be a halogen. So usually bromine, chlorine, iodine is the most common leaving group. So you're going to mix these things together. So plus two separate things, and mix them together. And the product of the reaction is going to be the nucleophile becomes connected to that sp3 hybridized carbon. Plus there's a byproduct, which is the leaving group, which is left. The leaving group gets separated out. It gets substituted out. So this reaction is a powerful way to replace a leaving group with a nucleophile of your choice. Let's take a look at a real example that isn't all this abbreviation. So let's take a look at a real case example. So let's say we have this molecule here plus ethyl bromide. Okay, real quick, before we figure out what the products are, let's identify which one is the nucleophile and which one is the electrophile, because all of these reactions, like we talked about in the previous lesson, are going to involve reactions between nucleophiles and electrophiles. And so if you remember, one of the key hallmark features of a nucleophile is a negative charge. So if you see a negative charge, that is going to be your nucleophile for sure. One thing that we saw explicitly in the previous lecture is that lone pairs on sulfur, whether they're neutral or negative, are nucleophilic. So this is going to definitely be our nucleophile. And then we're adding our electrophile, which meets the special criteria of the Sn2 reaction. Specifically, we have an sp3 hybridized carbon here connected to a leaving group, in this case bromine. And this, of course, is an electrophile because we talked about having anything attached to a neutral halogen is an electrophile. And the mechanism arrows for this reaction look very simple. The lone pair that are nucleophilic are going to attack the sp3 hybridized carbon. So there's always two arrows in an Sn2 reaction. The first arrow goes from the nucleophile lone pairs to the sp3 hybridized carbon. And then there's a second arrow that breaks the sigma bond between the carbon and the leaving group. Okay, now we can draw the product of this. And we have our sulfur now attached to our carbon. And we have a leaving group, which is bromine. So let me just sort of highlight the two components so that you can see how they got connected together. So I'll highlight my nucleophile piece in green, and I'll highlight my electrophile piece in orange. And you can see here that the green component became connected to the orange component, just like that. And then, of course, the leaving group is dissociated. So the key bond that we make in an Sn2 reaction is a new carbon nucleophile bond. In this case, it's this bond right here between the green and the orange. This is cool. This reaction is simple, but it allows us to make new bonds, and reactions that allow us to make new bonds are incredibly important in organic chemistry. Now, one thing you might want to keep in mind, you'll notice that in the reaction we have the green thing on the left and then the orange thing on the right, but in the product I put the orange thing on the left and the green thing on the right. That's okay. You could just as easily have written this. This is going to be the exact same compound if I write it like this. And neither one is preferred over the other. They mean the exact same thing, and you can see that this is just the result of the green being on the left now and the orange being on the right. Either way, same connectivity, same topology, so it's the same substance. Let's take a look at another example. Okay, what if we have this guy here? And why don't we add ammonia? Okay, first things first, let's try and identify our nucleophile. One thing you want to do when you're trying to find a nucleophile is draw in all the lone pairs in both molecules. And I can see that we've got lone pairs on halogen and we've got lone pairs on nitrogen, which is nucleophilic. Remember that lone pairs on halogens are only nucleophilic if the halogen has a negative charge. So that means that the nitrogen lone pairs, those are nucleophilic. So if you're forgetting this, review back, I think 2 pages. So like go back to the last lecture and we talked about these more rules, and we saw that lone pairs on nitrogen are nucleophilic if neutral, but lone pairs on things like iodine are only nucleophilic if they're negatively charged. So that helps us identify here that our nucleophile is the NH3 this time. Doesn't matter if you list the electrophile first or the nucleophile first. I like to mix it up just to confuse you. Okay, and now let's draw a mechanism. So the arrows are going to originate from the lone pair of the nucleophile, and where are they going to go? A common student error is to point towards the leaving group. No, the nucleophile is not attracted to the leaving group, not in the slightest. The nucleophile is attracted to the carbon that the leaving group is attached to. So the nucleophile attacks the carbon that the leaving group is attached to, and then there's another arrow showing the sigma bond between the carbon and the leaving group breaking. We do that. And now the leaving group is displaced. Our leaving group minus. And our NH3, we may need to calculate the formal charge there. We've got a nitrogen making 4 bonds, so that is going to have a formal positive charge. And of course, we could always check the charge thing always gets students confused. So just look at this. The starting materials, what's the overall charge of the starting materials? Neutral. There's no charge in either of the starting materials, so the overall charge of the starting materials is neutral. Now looking at the products, what's the overall charge of the products? Neutral. There's a positive and a negative, but they still cancel out to be neutral. So if your starting materials are neutral, your products should also be neutral. If your starting materials have an overall negative charge, your products are always going to have an overall negative charge. So make sure that you preserve charge. If you're not preserving charge, you're making a mistake. Okay, cool. So there's another Sn2 reaction. So I just want to flip on to the next page and show you that there's actually several ways to write an Sn2 reaction, and they're all equivalent. Okay, let's take a look at 3 different ways to represent the exact same reaction. I could have sodium ethoxide plus ethyl bromide produces this ether plus sodium bromide. Notice in this case, I'm actually drawing in the spectator ion of sodium. We'll talk about that in a second. Let's see another way to represent this reaction. I could split the ionic compounds up into the ions. So I could have the Na plus, the OCH3 minus, plus ethyl bromide produces this ether plus Na plus Br minus. So this is identical as the top case. I'm just drawing in the charges for the ionic compounds, if any. Here's another way I can write the same reaction. I could have ethyl bromide, and then I can draw the arrow, and then right over the arrow I can write the other ingredient. I'll do NaOMe. I'll abbreviate the CH3 as a methyl group this time. So anything over the arrow, below the arrow, or to the left of the arrow is considered a starting material. So it doesn't matter that the NaOMe is written over the arrow. It counts as being a starting material. It's just space saving. So on the page, it uses up less space because you're basically putting everything compressed. And then we can draw our product as this. Okay, all 3 of these ways is representing the exact same thing. So all identical. And I don't want you to be freaked out by the sodium in there, so I just want you to recall that there are ionic compounds that can participate in organic reactions, including the Sn2 reaction. So recall this, that lithium, sodium, potassium, and cesium compounds with nitrogen, oxygen, halogen, which is oftentimes abbreviated X, and sp hybridized carbons are ionic, which is why you sometimes see the plus and the minus. So for example, lithium tert butoxide is very common, so that would be lithium plus, O minus, and then there's a tert butyl group attached to the oxygen. Sometimes you'll see that written like this, LiOTBU, lithium tert butoxide. Another common thing you'll see is potassium cyanide, so like K plus, Cn minus, the cyanide ion. That is a ionic compound between potassium and an sp hybridized carbon. You'll see that sometimes written as KCN. So this should be review. You should know that there are certain compounds that are ionic, and these sort of compounds are typically nucleophilic because they have a negative charge. And the metal, like lithium, sodium, potassium, cesium, is just a spectator ion, so it's not actually participating in the reaction. Okay, so this is all well and good. There's some Sn2 reactions. These 3 are all the same ways of representing the same thing, but it turns out that the Sn2 reaction has some secrets. It has some mysteries. It's not as simple as simply replacing a leaving group with a nucleophile. There's more magic to it than that, and I want to take a deep dive into that magic right now. So the first magical thing that people discovered about the Sn2 reaction is that they have a property called stereospecific. Sn2 reactions are stereospecific. Let's take a look at an example of what I mean by that. So let's say I take this nucleophile, sulfur-based nucleophile, and react it with this electrophile that happens to be chiral. For practice, you could assign R or S to that stereocenter right here. This is a chiral electrophile. And if we're going to do an Sn2 reaction, remember that the lone pairs of the nucleophile are going to attack the sp3 hybridized carbon attached to the leaving group, and then there's going to be a second arrow that shows the leaving group being ejected out. And we go forward here, and what's going to happen is that the sulfur is going to come 180 degrees, or opposite, from the leaving group, so that in the product, the sulfur is coming in from the left. The leaving group is leaving on the right. Seems like it makes sense, right? The sulfur is over here on the left, the leaving group's here on the right, and they're going to come from opposite sides of each other. So after the reaction, we're going to get this product here. Plus, what's the byproduct? Br minus. The leaving group is on its own. Okay, this doesn't seem too unusual, but let's do something kind of interesting here. Let's take this product here and flip it 180 degrees so that it resembles more closely the starting material and see what happens. So flip 180 degrees. And so if we do that, I'm just going to pick up the sulfur and flip it around to this side, just like picking up the molecule and turning it 180 degrees. And so if I do that, this methyl group and the sulfur are going to flip places. Okay, but also what's going to happen is that the wedges and the dashes, they are also going to be flipped 180 degrees. So now the H is in front and the ethyl is in the back. And so if you compare the original starting material and the final product, what the chemist found was absolutely fascinating. It's that the wedge and the dash flip after an Sn2 reaction. There is a stereochemical inversion. Fascinating. What this means is we are not only changing the bonds in an organic molecule, but we're also changing the 3D arrangement of these bonds. We are flipping a stereocenter from being wedge dash to dash wedge. And this is called inversion. Stereocenter is flipped. So the big question, of course, is why? And also how? What's especially exciting about this finding is that it doesn't just happen some of the time. It happens 100% of the time that you do an Sn2 reaction. In fact, it's impossible to do an Sn2 reaction without flipping the stereocenter at the site of attack. Now, it doesn't flip all the stereocenters. It is smart enough to only flip the stereocenter that's connected to the leaving group. It has nothing to do with smart. It has everything to do with the mechanism. So the answer to how and why is something called backside attack. And this involves us taking a very close look at the mechanism. So let's say our nucleophile, instead of being the sulfur thing, is a cyanide ion. Okay, so there's a cyanide ion. And then let's draw a good electrophile, sp3 hybridized carbon attached to a leaving group. And let's draw the mechanism here. So the lone pairs on the nucleophile are going to attack the sp3 hybridized carbon, and there's going to be another arrow showing the ejection of that leaving group. Now, when we get to the product, what you're going to find is that because the nucleophile comes 180 degrees to the leaving group, that now our product is going to look like this. And so the key is actually to look at the transition state of this reaction. That is the halfway point between starting materials and products. If you watch this reaction on super slow motion and watch the two molecules come in, you watch the cyanide enter, you watch the chlorine leave, right at that halfway point, we call that the transition state, and we can draw that like this. So at the transition state, the carbon is being flanked by the cyanide group, and the chlorine is sort of leaving at the same time. The hydrogens, however, which were once cup-shaped, flatten out completely. So try and imagine, it's hard for me to draw it actually, but try and imagine that the hydrogens on that carbon are flat like a board. And you've got the, I'll actually show you guys in live lecture an animation of this happening and you'll see it. But basically the hydrogens act kind of like an umbrella getting inverted in the wind. They start cup-shaped, they end up becoming flat, we're talking about the hydrogens here, and then they break backward and face the other direction, cup away from their original direction. And so I'm putting this in brackets to show that it's a transition state, and there's also an equal sign with a line through it. If you ever see that, it's called a double dagger. That means transition state. And so the transition state leads us to this product. And so that's why we have inversion of the stereocenter. It's because the groups that are attached to the carbon become blown away like an umbrella opened too far and end up inverting into the opposite direction. And this is because of electron-electron repulsion. The nucleophile has a cloud of electrons around it that is pushing the other bonds away from it. Kind of like the wolf that blows down the piggy's house. You can kind of imagine it like that, is that if you have enough energy, you blow the bricks of the house down and you flip them over. And the result of this is a stereospecific property called inversion. Stereochemistry changes after the Sn2 reaction. Okay, so that's a cool little fact about the Sn2 reaction. We'll look at examples of that. Now, the next thing we want to talk about are the factors that affect the rate of an Sn2 reaction. It turns out that there's a lot of different things that can make an Sn2 reaction favorable or unfavorable. And I want to look at some of the properties that make an Sn2 reaction favorable. It turns out it's not enough to just have a nucleophile and an electrophile. A lot of times that sort of reaction is so slow that it doesn't happen in a time period that's appropriate for our lifespans. We want to talk about reactions that happen in a few minutes or a few hours. If a reaction takes 20 years, well, that's not very useful to us. So what factors influence the rate of Sn2? And we're only going to talk about two things today, and then we'll talk about two things next time. The first two things that we're going to talk about today are sterics of the substrate. And when I say the word substrate, I'm referring to the electrophile. That is the molecule that has carbon attached to a leaving group. We'll talk about the sterics of that substrate affect the rate dramatically. The second thing that affects the rate of an Sn2 reaction is leaving group ability. And this makes total sense, right? Not all leaving groups are the same. Some leaving groups are much better at leaving than other leaving groups. And so if the leaving group is really good at leaving, it's going to increase the rate of the Sn2 reaction. We'll talk about what the best leaving groups are and what some of the more crappy leaving groups are. Number 3, nucleophile strength. And we won't talk about this today, but we will talk about this on next lesson. Okay, this is another no-brainer. The stronger the nucleophile, the more quickly the Sn2 reaction will occur. And then number 4, and this is not so obvious, the solvent. Solvent affects the rate of the Sn2 reaction. That may not be so obvious. In fact, let me just go back a page and show you why the solvent has an effect. But again, we're going to talk about this next lesson. If you look at the transition state, it's a polar transition state. So, oops, I've closed it. What have I done? I've closed it. There we go. If you look at the transition state, it's polar. So we have a partial negative charge on the carbon, a partial negative charge on our leaving group, and we have a partial positive charge on our carbon in the middle. Okay? So because the transition state is polar, that means polar solvents are going to better dissolve the transition state. So it turns out the Sn2 reaction does a lot better in polar solvents because of the transition state polarity. Again, something we'll talk about later on. But let's just start off with substrate sterics, which is perhaps the most important influencer of the Sn2 reaction rate. And there are two things to consider with the substrate sterics. Again, the substrate referring to the electrophile with the leaving group. And the first thing that's important to remember, the carbon attached to leaving group must be sp3. I love to trick students by showing an Sn2 reaction where the carbon that's actually attached to the leaving group is sp2 or sp. In that case, the Sn2 reaction flat out fails 100% of the time. It is a requirement of the Sn2 reaction for the carbon attached to the leaving group to be sp3 hybridized. So don't let me trick you there, okay? Okay, the two things we need to consider when it comes to substrate sterics, the first thing is a more direct thing, and it's the degree of substitution. It's the degree of substitution, which is another way of saying how many other carbons are attached. Let's take a look. So first, the ranking is going to be that methyl is the fastest, followed by primary, followed by secondary, and tertiary is extremely slow. Okay. Methyl is the situation where there are no other carbons attached to the carbon that's attached to the leaving group. Primary means that there is one carbon attached to the carbon that's attached to the leaving group. So if you look at this molecule right here, this is the carbon that's attached to the leaving group, and attached to that carbon is one other carbon. Here's another example of we're moving forward into secondary. So that would look like this. Now attached to the carbon that's attached to the leaving group, there are two carbons. So that is a secondary substrate. And then the slowest of them all is the tertiary substrate, which looks like this. Now there are three carbons attached to the carbon that the leaving group is attached to. I'll just say here, Sn2 all but impossible. And so why is this the case? Why is the rate better for methyl versus tertiary? Well, let's take a look at the mechanism again. If you have a carbon attached to a leaving group, and attached to that carbon you just have hydrogens, well, hydrogens are very small. Now, this teeny tiny itsy bitsy eeny weeny baby sized atoms. So when the nucleophile comes, there is no barrier to getting backside of that carbon and displacing the leaving group. However, imagine now that carbon is attached to three other carbons. And of course, I actually need more room because this is so crowded here. Let's see if I can do a better job here. So the carbon attached to the leaving group. Now each carbon that's attached to that leaving group, so the carbon that is attached to the leaving group has three additional carbons attached to it, and each one of those carbons has three hydrogens attached to it, let's say. You can see that the level of crowdedness increases dramatically. The nucleophile still has to wiggle its way in through the back. And look at how it has to navigate this tight passageway to get to that carbon to displace the leaving group. Makes this reaction extremely slow, because what are the odds for the nucleophile to be able to get into that central carbon? So you can kind of think of this like a game of football. I'm not really a sports guy, but you can imagine if you leave your quarterback undefended, the opposing team is going to very easily be able to get the quarterback. However, that never happens in football. In professional football, the quarterback is shielded by blockers that slow the attack of the defenders. We're going to come in and try and get that ball, trying to get that quarterback. They're not going to be able to do that because there's so much blocking going on. So this first case is very fast versus the second case is extremely slow. So you can see how this would affect the rate. It all has to do with that backside attack. Now, degree of substitution is not the only thing we need to consider. We also needed to consider beta branching. So degree of substitution is just counting the number of carbons attached to what we call the alpha carbon, which is the carbon attached to the leaving group. Beta branching is talking about branching beyond the alpha carbon, because those are also going to interfere with the nucleophile approaching. So if you draw a sample substrate here, the alpha carbon is the carbon that is attached to the leaving group, and the beta carbon is what's attached to the alpha carbon. So we're going to talk about branching at the beta position. And so if you have this molecule here, this is the alpha carbon and this is the beta carbon. How many carbons other than the alpha carbon are attached to the beta carbon? So if this is the alpha carbon and this is the beta carbon, how many carbons other than the alpha carbon are attached to beta? None. So I'll just write a little table here. Beta, 0. That's good. You don't want carbons attached to beta because that's also going to block up the backside. Let's compare that to this molecule here. Okay, now we've got alpha, we've got beta. How many carbons are attached to beta other than alpha? 1. So the beta branching in this case is 1. Here we have an example with beta branching of 2. And then we can also have an example, I'm just going to try and cut that off so we don't get in the way there. Beta branching of 3. We have 3 carbons attached to our beta carbon. That would be beta branching of 3. And so it turns out that branching at the beta position does slow the rate of an Sn2 reaction, just like branching at the alpha position does. And so if we compare the relative rates, if we set the rate of beta branching of 0 equal to 1, the rate is nearly cut over than half for adding 1 branch, down to 0.4. These are all just relative rates. If we add a second branch at the beta position, the rate drops dramatically to 0.0012. And a triple beta branch is very punishing. The rate drops down to 0.000012. Now you don't need to remember these numbers. You just need to know that as we increase beta branching, it's going to slow the rate down. And for the purposes of this class, substitution, so branching at the alpha position, is going to be the most impactful steric consideration. And only look at beta branching when you need to break a tie. So this order here is the most important thing, but if you end up with a tie, then look at beta branching to break the tie. Let's take a look at an example question. Okay, I've got 3 different Sn2 reactions here. They're all using the identical leaving group of chloride. And they all have a nucleophile of KCN. Let's determine the relative rates of these reactions where 1 is equal to the fastest. Okay, so first things first, let's determine the degree of substitution for each of these substrates. How many carbons are attached to the alpha carbon in A? How many carbons are attached to A? Now, I'm not asking how many carbons are down the line. I'm asking how many carbons are directly attached, bonded to that carbon. And as you can see, there's only 1 carbon. This carbon here is the only carbon attached to alpha. So the substitution is primary. And what about the beta branching? What's the beta branching here? Well, look at the beta carbon now and how many carbons are attached to beta other than alpha. Just 1, 2. Don't worry about the double bonds. There's just 2 carbons attached to that beta carbon, this one and this one. So beta branching equals 2. Take a look at the next molecule here. Taking a look at the alpha carbon, how many carbons are attached to it? 1, 2. So this is a secondary substrate. And what about the beta branching? This molecule is interesting in that there are 2 beta carbons. There's a beta carbon here, and there's a beta carbon here. Look at each of them. Whichever one has the most beta branching is going to be your determiner. If they're, in this case, they're tied, we'll see that. But whichever one has the most beta branching, set that equal to your overall beta branching. Don't add them up. So for example, this carbon here, which is one of our beta carbons, how many carbons is it attached to other than alpha? Just the 1. So the beta branching for this beta carbon is 1. And what about this beta carbon? How many carbons are attached to it? Also just 1, this guy down here. So the beta branching equals 1. What about this reaction here? Well, the degree of substitution is primary. There's only 1 carbon attached, but what is the big deal with C? The carbon attached to the leaving group is not sp3 hybridized, so this one fails. No reaction. C attached to leaving group is not sp3. So that one is for sure going to be the slowest because it's impossible, right? You can't get slower than never. So reaction C is the slowest. Then it's between A and B. Which one's faster? Remember that we look at the alpha carbon branching before we consider beta branching as a determiner. So it turns out that A is a primary substrate versus B, which is secondary. That's more important than reducing beta branching. So that means that A is going to be the fastest. And B will be the mid-range. Okay. Now, if there was another option D that was primary and had beta branching of 1, that would beat out even A, because it's another substrate that's primary, but if the beta branching is less than 2, that's good. So if the beta branching were 1 or even 0, that would be ideal, and that would be faster than even A. Okay. Awesome. So that's what you need to know about substrate sterics, and we'll look at a lot of examples like that. Okay, last thing to talk about today is going to be leaving group ability. Don't we love our leaving groups? Now, one thing that's nice about the leaving group abilities is that they trend the same as acidity. Meaning the strongest acids are also the best leaving groups. So for example, if you look at your pKa table, one of the strongest acids, in fact, the strongest acid on your list is HI, hydroiodic acid. And we know it's the strongest acid because it has the lowest pKa of -10. Then after HI comes HBr, has pKa of -9, HCl, which is -7, H3O plus is another very strong acid, the hydronium ion, which is -2. Also on your pKa table, there is the sulfonic acid, which is -1. And then we have things like hydrofluoric acid, which is +3. So these are some of our stronger acids. Okay, and so this trend helps us determine the leaving groups. So the best leaving groups are the weakest conjugate acids. In other words, are the weakest conjugate bases. They come from the strongest acids. So the best leaving group is I-. That's the best one in this class. It's an amazing leaving group. Followed by Br-. Still great, but not as good as I-. What do you think's next? Cl-. Followed by, what's the conjugate base of H3O plus? Lose 1 proton, you just become H2O. H2O, water, is a phenomenal leaving group. Still not as good as the previous 3. Another great leaving group is the sulfonate leaving groups. Those have this generic sort of formula where you have sulfur, Oxygen has a negative charge. That's called a sulfonate. Those are great leaving groups. And those are all much, much better than things like fluoride, which start to become pretty crappy leaving groups. So that means if you ever forget the order of leaving groups, you can just look at the pKa table and look at, okay, if the pKa is really low, the conjugate base is going to be a really good leaving group. And so we can sort of rationalize this by reviewing acidity trends. And the rationale is exactly the same. In an acid-base reaction, what's essentially happening is you have a base reacting with an acid. So the base usually has a negative charge, and it's reacting with an acid, which is just an H attached to some leaving group, like bromine or iodine, HI, hydrochloric acid, for example. And then in the acid-base reaction, the base, lone pairs of the base grab the proton and eject the leaving group, which ends up being the conjugate base. And then we end up with base H, which is the conjugate acid, plus our leaving group gets ejected. Okay. In an Sn2 reaction, you can see it's very similar to an acid-base reaction. Instead of a base, we have a nucleophile. And instead of grabbing a hydrogen, it's grabbing a carbon attached to the leaving group. This is the organic version of an acid-base reaction. That's all Sn2 is. The nucleophile grabs a carbon instead of a hydrogen, but it still ejects a leaving group. And then the result is having the nucleophile carbon bond forged, and we still get the leaving group ejected. Okay? So the idea is that the more stable the leaving group, the better. And this is totally an analogy. If you remember back in the previous lesson, we were talking about being a relationship coach. And we were trying to say, like, we could determine how strong an acid is by looking at its leaving group stability, or the conjugate base stability. So if the conjugate base, or the leaving group, is very stable, that's going to make it a very strong acid. Similarly speaking, if the leaving group is really good, it's going to make it a very strong substrate for Sn2 reaction. Okay, so there are, let's see, 3 trends to keep in mind for these leaving groups. So the first one is the periodic table trends, which I'll just call periodic trends. And so if this is your periodic table, the best leaving groups are to the right and down. Okay, so horizontally, what we care about is electronegativity. So when a leaving group leaves, it takes electrons with it. So you want something, if you're going to have a good leaving group, it should be electronegative, meaning it should be able to tolerate the extra electrons it's going to gain. So for example, fluoride is a better leaving group than hydroxide. And the reason for that is that F is more electronegative than OH. Vertically, the reasoning for leaving group is atomic radius. And there's kind of 2 ways to think about it. But the way I kind of like to think about it is this. Imagine you have hydroiodic acid, which you know is a very strong acid, HI. The H atom is very, very small, and the I is very, very large. And so there's poor overlap, meaning that the electrons, they can't be shared very efficiently because I is so dang large compared to H. The size is just a mismatch. So there's poor overlap, so the I minus can't hold the H well. That makes the I a really good leaving group. Poor overlap. I minus can't hold H or carbon very well. Okay, obviously, the leaving group, the weaker it holds onto the carbon, the easier it's going to be to leave. So if you have a really big, dumb leaving group, it's a great leaving group because it just gets knocked off so easy by even the weakest of nucleophiles. So big is good for leaving group. Next thing to consider, formal charge. All else equal, assuming all else is equal, a positively charged leaving group is going to be better than neutral, which is going to be better than negatively charged. So if you have carbon attached to a positively charged leaving group, that is going to be better than neutral, which is going to be much, much better than a negatively charged leaving group. Now, keep in mind that these charges we're talking about before the leaving group leaves. We've seen a lot of great leaving groups that are negative after the reaction, but we're talking about the charge of the leaving group before it leaves. And the reason is that when the leaving group leaves, it's going to gain electrons. So if something is positively charged, it can relieve its positive charge by gaining electrons. If something is negatively charged, it's not going to want to gain any more electrons because then it's going to become doubly negatively charged, which is really bad. So why? Leaving group gains electrons when it leaves. For example, let's just look at an acid-base reaction as an example. Okay, so in this case, the base is going to grab the H of the hydronium, and the leaving group has a positive charge. The atom that's leaving has a positive charge. It makes it a pretty good leaving group because when it leaves, it becomes neutral. Which is nice. So formal charge can impact leaving group strength. The last thing to consider for leaving group strength is resonance stabilization of the leaving group. Take, for example, the following acid-base reaction. And again, acid-base reactions and Sn2 reactions are totally analogous. The only difference is instead of grabbing an H, you're grabbing a carbon. So consider a base reacting with water versus a base reacting with sulfuric acid or a sulfonic acid. Okay, in the first case, the base grabs the H, kicks out the leaving group. Second case, the base grabs the H, kicks out the leaving group. Now let's take a look at the products of this reaction. I'll draw the double-headed arrows, I guess, because it's an acid-base reaction. And we have the base getting an H. Should have an overall plus charge after that. Plus the conjugate base, which is hydroxide. Compare the bottom case scenario. We have a base attached to an H plus our conjugate base this time. Now it can participate in resonance, right? You can draw a lone pair next to pi, et cetera, et cetera. So this is resonance stabilized. And this is not resonance stabilized. So that makes the sulfonate a much, much, much better leaving group than hydroxide. You'll notice that they both don't have a formal charge. They're both neutral leaving groups. They're both the same atom, right? They're both an oxygen-based leaving group, so we wouldn't use periodic trends. So the only way that we can rationalize the difference in leaving group strength between hydroxide and sulfonate is that the leaving group of sulfonate is resonance stabilized. So it's much easier for it to leave and then do its own thing versus hydroxide, which leaves and has no stabilization. Okay, so these are all the trends. Let me just give you the grand order of leaving group, and then we'll call it a day. Okay. The very best is going to be on the left, and the very worst is going to be on the right. So as I mentioned before, I- is the best, followed by Br-, followed by Cl-, followed by H2O, followed by sulfonate. Okay. Then I'm actually going to draw this as our cutoff. So after this point, there's going to be no Sn2 beyond this point. Meaning all the subsequent leaving groups that I'm about to list are too poor for Sn2 to occur at a reasonable rate. Meaning that you only need to remember the 5 good leaving groups. So the only leaving groups you need to remember are iodine, bromine, chlorine, water, and sulfonate. All these other ones are crap leaving groups that are not going to work in Sn2. And they are F-. Doesn't do Sn2, not a good leaving group. Next up, acetate. Okay, and this is in order of getting bad to worse. Okay? Cyanide. I'm you know what, just to save space, I'm not going to put my negative charges in circles, just to save space. Next up, sulfide ions, like SCH3- or SH-. These guys are absolute crap leaving groups, but not as bad as oxygen-based OCH3- or OH-. I'm running out of room here a little bit. Let me just scoot it all over a bit, because there's a few more I'd like to show you. The Hall of Fame of crap leaving groups. Next up, NH2-, dreadful leaving group, absolutely terrible. And the mother of all bad leaving groups, H-, just really does not like to be a good leaving group. Okay, so here's a bunch of bad leaving groups. They won't work in Sn2 reactions, so don't try and substitute them. The only good leaving groups, the ones you want to look out for, are over there in red. Okay, so let's stop right there, and then next class we're going to talk about how 2 additional factors, nucleophile strength and solvent identity, can affect the rate of an Sn2 reaction. Okay, bye for now.